Well, good morning or good evening, whichever time you happen to be watching this lecture. I'm sorry I have not been able to give you an in-class lecture today. I have to cover one of my colleagues' classes, which overlaps at the same time as yours does. So I felt it was best to perhaps put this lecture into an online capacity where you can watch at your earliest convenience. Today we're going to be talking about sedimentary environments. This is the first of a series of lectures where we're going to be talking about where sediment is deposited. We're going to be talking about alluvial fans, rivers, and deltas in just a few minutes. Now, a word of warning, two words of warning actually. The lecture you're about to see is one that I did last year in the fall of 2010. I've just taken the voiceover for that and added it to the slides for this year. So there may be some stuff that we talk about there that may not be exactly in sync with what we did this year, but it's minimal, and for the most part they can overlap quite nicely. The other thing, which is actually more relevant at this point, is that when you do a voice-over narration at the start of a lecture and then merge it with an audio file from some other source, there's often a very sudden and dramatic change in the volume. So if I were you, I would turn the volume down on my computer now just a little bit, because in about 5 seconds it's going to get pretty darn loud. That 5 seconds will be when I count to 5. 1, 2, 3, 4. I'm serious now. Turn the volume down. 5. Enjoy the lecture. Last time we covered the first two items here, and I've got them checked off here. We did the types of sediment, sedimentary rock classification. We did not get through sediment transport. That's what I'm going to come back and talk about, because I want you guys to have an understanding a little bit about how sediment is moved from one place to another. Okay, so quickly a recap of the first two items. We reminded ourselves of the different types of sedimentary rocks that we have. There are 4 major classes: siliciclastic, biochemical, chemical, and organic. And this is a lovely shot. Isn't that pretty? Doesn't it make you just want to go for a swim in this organic goo? Oh boy, it's nasty, but I'll tell you, that's an important environment, because that's where you get a lot of organic material being produced. Hence the organic designation. This is going to be plant material. This is where coals come from. We talked about how sediments are classified. And this, again, the figures you see off this pages come directly from the Geology 111 lab manual, which is available online. A couple people emailed me previously saying that they had some problems when they were going over the slides in the PowerPoint format. Because you know, when I shrink these things down to put them online, a lot of the images just get really fuzzy and all. If you can't see some of the stuff, then I recommend you just turn right to the lab manual, because that's where basically I took them from. This diagram summarizes sediment size, sediment rock types, and again, as far as we're concerned with sedimentary rocks, we're really interested in the particle size. So we divide up everything in terms of the grains that make up the sedimentary rocks. This is in millimeters, going from fine up to coarse. We recognize 3 different sediment types: gravel for the coarse stuff, sand for the medium stuff, and mud, which consists of silt and clay, for the fine-grained stuff. Now, from your point of view, you can't see the mud-sized particles, even with the hand lens. You can see the sand-sized particles with or without a hand lens, and then the gravel size are the big ones that you can literally, pick out and throw at each other and cause much damage. These are the sediment names: mud, sand, and gravel. And the sedimentary rocks that are made from them, at least as far as the siliciclastic ones are concerned, are mudstones, which can be divided into siltstones and claystones, sandstones, and conglomerate of breccia based upon particle shape. We talked about particle shape as well as the sorting and the overall rounding. Talked a little bit about what kind of variables are causing this, okay? And this was to give you some clues as to the types of information that sedimentologists, those people who study sedimentary rocks, can get out of the rocks when they look at them carefully enough. This is the chart that, again, is in your lab manual. This is the whole thing now. All right, these are all the rocks you're going to see when you get to the sedimentary rock component. There's a lot more rocks now than you did when you saw in the igneous rocks. But I'll tell you this, from my personal reflection, most students have the most difficulty with the igneous rocks. If you're doing well with the igneous rocks now and do well with your test, you're in fine shape. Sedimentary rocks, as abundant as they are more intuitive to us, because we live in an area where there's a lot of sediment. You understand how the sediment works here a little bit better. Looking at igneous rocks, which come from volcanoes and under the subsurface, that's a little bit harder for people to visualize if they don't have a volcano in their backyard. Okay, so the sedimentary rocks generally are easier to do for most students, even though there's a lot more of them. As long as you remember that they're divided up according to class, grain size is an important variable for at least 2 of the different classes, and then it's just a matter of recognizing the individual grains that make them up. Sediment transport. Sediment transport is where we remove material from one place and move it somewhere else. The best way of illustrating this is to look at a simple cartoon diagram as you see here. Now this diagram you've kind of seen previously when we were talking about the soils and weathering. So what we have here now is a place where there is a source of material. In this case, call it a mountain. And by the way, these little plus symbols you see here, that's the standard geological symbol for granite. You're going to see that a little bit later on when we get into geological maps. When we were talking about soil development, we were talking about the idea that if you have rock exposed at the surface of the earth, the rock is going to start to break down according to whatever weathering reactions you have. Physical weathering is going to break the material into smaller particles. Chemical weathering will actually chemically change the material. We talked about the idea that if you start off with the granite, the only thing that's chemically stable over time is going to be the quartz grains. You lose the orthoclase, the pink stuff. You lose the biotite, the hornblende, the dark stuff, because they break down to other materials. They ultimately turn into soil or regolith, depending upon what kind of processes are taking place there. The other variable we have to consider is that not all of the stuff that is breaking down by weathering reactions is actually staying at the source. Some of it is being moved, transported from the source down to some other place. Now the proper terminology we use here is source is where the material comes from, the sink is where it ends up going. Now we can see this here very simply. All you have to do is go down to Dolphin Island or Mobile Bay. Dolphin Island is full of sand grains. Mobile Bay is full of fine-grained silt and clay or mud. Where did all that stuff come from? All right, where did it come from?
River wash out from.
Rivers. And where did the rivers come from? That way, right? Rivers flow downhill. And when they flow downhill, they're bringing material with them. They are the transport mechanism. But it's not just rivers that are the transport mechanism. We can have wind doing it. We can have ice doing it, depending upon where you are. The sink is anywhere where sediment ends up. Okay. All right, so the beach or Mobile Bay or a desert, and that's what we're going to talk about a little bit later on, are all the various sinks that are out there. We call them depositional environments, as it turns out, okay? But the point is, this sediment came from some source, and it's changed along the way. So transport's an important mechanism that we have to talk about here a little bit. Now here is an example of sediment in motion as we speak. What you're looking at is a nice aerial shot. We're going to come back and look at this, this image again in a few minutes when we talk about the specific depositional environment. But we're flying over California. This is a part of the mountain range, the Sierra Nevadas. It doesn't look like a mountain range through here because it's kind of flat projections through the camera. What you see is basically a dry river coming out here, and then all of a sudden the river spreads out. This is all sediment that has been deposited in a very large fan-shaped structure called, surprisingly, an alluvial fan. All right, so here what we see is material being derived from the source and being transported and deposited at the sink. Not very far away, as it turns out. It's probably 5 miles from here to there. And in 5 miles, think about it, how much weathering is actually going to take place in the rocks? Not much. How much transport or how much rounding is going to take place with the sediment that's being moved in only 5 miles of transport? Not much. So you would predict, and you'd be correct, saying that the material here is just broken up bits of material that comes from here. It looks very much like it. So it's going to have orthoclase in it. It's going to have biotite in it. It's going to have quartz in it. It's going to have a lot of stuff. It hasn't had a chance to break down all that much. That's an important thing to consider because it means the sediment being moved from one place to another is going to vary depending upon the amount of transport that it's had as well as the amount of weathering that it's had. Here's another effective way of moving sediment. And this is one that, of course, certainly affects where we are. Rivers. Now, this is actually a rather tranquil shot. I believe it's out of Missouri somewhere. Lovely green hills. The water looks relatively clear. But you know, if you go to any river around here, you don't see clear water. Has anybody ever seen to the bottom of a river channel in a river that's flowing effectively around here? Because it's muddy. It's full of yucky stuff. It's not yucky, incidentally. It's just sediment material. So the rivers are transporting material. And the rivers are very much more important than alluvial fans are in terms of transporting material where we are, because of the fact that they are everywhere and they are constantly flowing. Now, rivers are really important mechanisms, and I want to focus a little bit on how sediment transport actually works in this media. If you're looking at a river, this is a cross-section through a meandering river channel. We're going to come back and talk about this in a few minutes too, okay? What you're going to see is the water is constantly moving. And as it is moving material in three different ways. The stuff you will seldom see, unless you go swimming in the water and dump down right to the bottom, is the stuff that is being transported along the bottom of the stream, which is called the bed load. The bed load usually consists of the coarsest grain material, the sand, and in some cases the gravel. All right? It is because along the bottom here, this is where the current is moving the fastest. And you should be able to predict this, that there's a relationship, that the faster the water is moving, the coarser the sediment that it can carry. If a river is flowing very slowly, sand can't move because it's too heavy to be moved. It stays behind. But if the river's flowing fast enough, it will take the sand grains and move them along the bottom of the river channel. That's called the bed load, and it's the coarsest grain stuff that the rivers can carry. Don't forget that there's also a significant amount of fine grain material. Clay minerals like kaolinite. Where did the kaolinite come from? All right, the breakdown of minerals like feldspars. All right, when they start to break down, they get converted into kaolinite. That's a finer grain material. Those particles are so small that literally, once they get started to move in a current, they don't settle until they get to a place where the water is absolutely stagnant or not moving at all. Now, in a river, even a river that's moving very slowly, that's never going to happen. The only place those clay minerals can actually settle out is when you get it into the middle of the ocean, and literally the currents aren't moving at all and the particles can settle. It might take them months to years, incidentally, to go from the top down to the ocean floor. Mobile Bay is a little bit more stagnant, so it'll come a little bit faster there. So you get the idea now that rivers consist of stuff being moved along the bottom, the bed load. They also consist of the stuff that is suspended, constantly moving in suspension, which is the fine grain material, the clay and the silt. And there's one more important variable that we have to consider in terms of transport. It's the stuff that dissolved out. Don't forget that there's a significant amount of chemical dissolution that takes place in rocks as well. And again, it's not just salt. It's limestone and various minerals that when they weather turn entirely to ions. And indeed, if you were to analyze the average composition of river water down here, you'd find it's enriched in calcium, in magnesium, in carbonate. It's a chemical soup. That stuff gets washed into the oceans as well, but it's being transported as dissolved components. Some rivers, incidentally, consist of more of this than they do of these two, to the point where you can't drink the water. It's got so much dissolved calcium carbonate in it, okay? These rivers are an effective mechanism of transporting material from the source, wherever the rivers come from, down to the sink, wherever they flow into it. And along the way, they're going to be depositing some of the sediment as they go, and where they deposit the sediment is ultimately going to be the different types of sinks that we're going to be dealing with. Okay. All right. Along the way, sometimes you actually see some evidence, some record of the fact that sediment was moving. A classic example are ripples. Now, most of you have seen ripples when you walked along the beach. Have any of you actually walked along rivers? Rivers that might have, been flowing a little bit higher in the past and the water's dropping because, rivers rise and fall. Often you'll see right along the shore or right along the edges of the river, you'll see little ripples. That's because what happens is when the bed load is moving along the bottom, it's not normally moving as sediment just going along as a sheet. The sediment's rolling around, and the very nature of this transport mechanism deposits it into these so-called ripples. Now, these are what they look like. This is in a tidal flat, okay, which shows you beautiful ripples ripples going as far as the eye can see. The ripples that form in rivers tend to be rather asymmetrical, and they show you a current direction. This, again, is really important information if you're a sedimentologist trying to reconstruct what was happening in the past. We can look at sedimentary rocks that contain remnants of these ripples and determine which way the current was flowing at the time the sediment was formed. That sediment may be 1 billion years old, and yet we can still tell which way the rivers were flowing, or in some cases, where the wind was blowing. Because don't forget, wind is also an effective transport mechanism. Maybe not down here, but if you live in an area where there are no trees, like desert areas or very arid regions, when the wind blows and you see those telltale sandstorms off on the horizon, that's an effective way of moving sediment from the source, wherever the wind's coming from, to where it's being deposited. And along the way, you can get huge ripples. Sand dunes in the desert are nothing more different than the small ripples you see along the edge of a stream or along the edge of an ocean, except that the wind has been blowing longer, the sand's been piling higher, and there's more of it to start with. It's the same overall thing. And yes, you can determine which way the wind was blowing by looking at the orientation of these ripples or dunes, like you see up and through here. As I said, a very powerful technique. And it's cool, because I've done this. I mean, I've looked at rocks that are 500 million years old, and it turns out that they formed in a marine environment where the currents were flowing from south to north, completely ass backwards to what we see today. And all it means is that 500 million years ago, the orientation of things were different. Paleogeography, the idea of looking at the way continents were configured in the past, is largely determined based upon evidence like this. Which way was the river in relationship to the rocks being deposited? Rivers only flow downhill, folks. All right? So if you find them flowing in the opposite direction, or evidence that the rivers flow in the opposite direction, it tells you the slopes were reversed sometime in the past. And perhaps it will surprise you, maybe not for the people taking Geology 112 now, but if we were to be standing right here now, 300 million years ago, we would have great rivers flowing from south to north, because behind us, where Dolphin Island is today, was a huge mountain belt getting larger and larger and larger, flowing into what was a great inland sea that was more or less right in the middle of where Montgomery is today. Things change over time, and we can largely reconstruct things like that because of looking at evidence like this in the rocks. All right, now that was the stuff I was supposed to get through last time, and it was because I was just I was so excited getting back, I just wanted to talk about other things and all. But now we still have a pretty big agenda on our plate here, because now what I want to do is I want to start looking at some of these different depositional environments. I'm going to define what a depositional environment is for you if you don't already know what it is. Then we're going to start looking at some of these things in a little bit of detail. Starting off with the various things that we looked at today. Alluvial fans. These are these fan-shaped deposits that form near mountains. We're going to talk about meandering rivers. We already saw a cross-section meandering river when we were talking about bed load, suspended load, and solute load. And then we're going to culminate in deltas. Now, the information that you can find for this is available on 2 of the web notes, 15A and 15B, and it's also in the lab manual in Chapter 3, okay? So a lot of these diagrams, again, come from that. Depositional environments. Okay, the proper definition for a depositional environment is here. It's basically where sediment's deposited. In other words, it's the sinks. And what we do is we recognize different types of depositional environments according to the conditions that are evident at the time of deposition in those sinks. So let me try to explain this as best I can, all right? You obtain sediment from erosion or through some other mechanism. It's transported into the area where it can be concentrated, the so-called sinks. And depending upon what conditions are going on at that time, you're going to get different types of materials. So case in point, if you look up here at the very top, where you see the alluvial fan designation, those are those fan-shaped deposits that form very close to the mountain. So in other words, the source and the sink are right on top of one another. But then you also have rivers that can transport sediment down into an oceanic environment. Now where the rivers meet the ocean, you get a big pile of sediment, very much like an alluvial fan as it turns out, called a delta. But it's a long way away from where the source of the material is. And again, you should start being able to make some reasonable deductions about what the nature of the sediment is going to be like between these areas. At the very top, where you're sitting on top of the source, you would argue not much chemical weathering has taken place. Down here, a long way from the source, a lot of chemical weathering has taken place. So you would argue correctly that down here what you're going to find are largely things like quartz and clay minerals. But up at the top where the alluvial fans are, it's going to be largely broken up bits of rock with a lot of orthoclays, a lot of granite fragments, etc. Along the way, rivers themselves can be sinks. Channels that are formed in a meandering stream environment, as you'll see, are capable of leaving sediment behind. And we can identify those types of sediments that have been deposited in the past as being associated with a meandering river. We also have beaches, estuaries, barrier islands. Up at the very top there you'll see desert and something called a sabkha. A sabkha is not something that is associated so much with rivers. They form in very dry areas, and if you think about it, if it's a dry area, you're not going to have many rivers, are you? But this is an environment where you might have a very flat region where seawater, during the tides coming in, is going to be exposed to very arid, dry conditions, in some cases very hot. What's going to happen to the seawater? It's going to evaporate out. What's going to be left behind? Whatever minerals happen to have been dissolved in the water. That's part of the chemical sedimentary rocks. What this diagram does for you is present many, not all, but many of the different types of depositional environments where sediment can be deposited. And it gives you an idea of the wide range of material that is possible out there. Now, once you know what the rocks are like in these environments, or once you know what the conditions are like, you can start interpreting which environments were responsible for the rocks that you find in the sedimentary record. That's what this part of the course is all about. We're going to talk about these environments. We're going to talk about the different processes operating in these environments. Then we're going to talk about the types of rocks you might expect to be found in these environments for those reasons. And then later on, if you happen to, oh, I don't know, maybe you're going for a walk in the Sierra Nevada mountains and you find a rock that's 500 feet above sea level, and it looks exactly like the sediment that you find in Dolphin Island today, you'll make the conclusions, hopefully, that no matter where the rocks are today, if they contain clues that tell you where they were deposited originally, that tells you the environment they were associated with. So if you find a quartz arenite sandstone, that's a sandstone composed exclusively of quartz grains, no matter where you find it, your first conclusion is going to be it was likely deposited originally as sand on a beach. And it doesn't matter if that rock is now 500 feet above an arid region of California. It means when the rock was deposited, however old the rock was, there was a beach there sometime in the past. That again is a powerful tool for reconstructing the paleogeography, things that were like in the past. All right, and lastly, a plug for my discipline. I'm a sedimentologist. This is what I do. I study the rocks. I come up with designations as to the type of depositional environments that were there in the past. Okay, so sedimentologists study sedimentary rocks, volcanologists study volcanic rocks, and metamorphic geologists study metamorphic rocks. I'm one of these guys. All right, now for today, what we're going to start off with is looking at some of these environments, starting off with alluvial fans up there in the hills, in the mountains. Here's a nice little cartoon sketch. Number one, shows you why they're called alluvial fans. Number one, they're fan-shaped, duh. And the fact that they're made of alluvial material implies that they are formed from material literally coming right down from the hills and the mountains. Now here you'll see, this is very much like the photograph I showed you earlier. There is the feeder channel going through the pass of the mountains, and then once you get to this point here, the sediment is deposited in a fan shape, and they can coalesce, giving you a whole bunch of these different things here, okay? So alluvial fans, fan-shaped deposits, formed at the base of mountains for reasons that we will get into in just a second. Here's some of the important information that you need to know about the types of sediment being deposited here. Number one, it will range from gravel to clay-sized. Now, for those of you that are thinking that, well, hang on, why would there be any clay minerals if there hasn't been any chemical weathering taking place, or at least not much? That's a good question to ask, incidentally. But you have to remember, in this environment, you can still have rocks being broken down physically. You can physically break rocks down into clay-sized particles. They may not be clay minerals. They don't have to be, as long as they're fine enough. But for the most part, this is an environment that is dominated by gravel-sized particles. And the gravel-sized particles here can be the size of this room. I mean, they're huge in some cases. They are angular to sub-rounded particles. Angular means has sharp corners. Now, why would that not surprise you? Why would you expect this to be angular, at least the particles?
Short distance.
Yeah, short distance. Sub-rounded means that some of the corners will break off because no matter how you deal with it, there's still water involved in some cases. Water still flows down here, so some of the particles will get rounded a little bit, but not nearly as rounded as you would find on a beach. And then lastly, in yellow, since this is the first time we've talked about this, we designate the mineralogy of these particles to be immature. Immature versus mature. Oh, I could say an awful lot about that in terms of just people's personalities, I suppose. But when it's applied to geology, it has to do with the amount of chemical weathering that has taken place on the rocks. A mature sediment is a sediment that has gone through a significant amount of chemical weathering. All right, it's largely broken down. All the weak materials, all the unstable materials have been broken down. The sand along Dauphin Island, which is largely composed of quartz grains, is said to be a very mature sediment. All the unstable stuff is gone. This is said to be immature because there's not much chemical weathering taking place. If this is granite, you'll find literally chunks of granite making up the gravel-sized fraction in this sediment. You'll find big chunks of orthoclase in this area. So you're going to find a rock that is going to be enriched in these unstable particles. So we say it is immature. That's an important thing to consider. And it means whenever you find a sandstone or a breccia, because it would be a breccia if you got gravel-sized components in it, chances are it's going to be something that formed pretty close to the source. All right, I'm going to show you some pictures of these things. And again, one of the nice things about being a geologist is that when you fly over things, you see stuff that kind of makes sense or something you talk about in classes. You sit there with your camera, which is why I took over 900 photographs flying over the Andes for 20 minutes when I was down there in Argentina. Anyway, here's another shot over the Sierra Nevadas. And this part of California is not all that pretty, but it still has some nice geology in it. If you look up in the corner and through here, what you're going to find is that you have an alluvial fan. There's an alluvial fan coming through here, but there's also more than just an alluvial fan in this environment. Here's the alluvial fan coming down from the mountains, and there's a stream. And then all of a sudden you see the thing shifting into this. That's because we have an alluvial fan that now joins up near the base with a normal river system. All right, so that's another thing you have to realize about depositional environments. They're not isolated. Everything passes laterally into something else. So the actual alluvial fan stops probably around here, and then this becomes part of a river system, which again is a standalone type of depositional environment. Here's the image that we saw earlier. I've moved it down here a little bit so you can see the classic shape of this. And this is a lovely image because what you see here are these bands, and that's more or less the horizontal surfaces. Water gives you another horizontal surface, so you can actually see the shapes of these things. We divide the fan into different components, okay? In fact, let me put this up here on the chalkboard, looking down now like this. That's the classic fan shape, okay? We normally divide it up into three components like this. This is called the fan head, middle fan, and the toe. Okay, so along those lines like that. And let me show it to you here in terms of these designations. There's the fan head at the very base. That's where it's narrowest at the highest elevation. There's the middle fan, and then there's the fan toe. Now, once again, this particular alluvial fan, if you look down towards here, you'll see, start seeing some rivers and all. This part down through here with the river flowing that direction, that's probably best called more of an alluvial plain. An alluvial plain just is anything that's flat. The plain means it's in the surrounding area, and it's often caused by rivers and alluvial systems. But again, you can almost absolutely see the designations here where the different components of the fan actually shift nicely. Here's the channel, the feeder channels that lead to the fan. So here's the fan in this direction, and you can see that what we have are rivers and things pouring right down from the mountains in all different directions, all coming together into one channel, which is the access point or the feeder point for the fan head. This is a classic image, because what you're looking at here, and this is not altered in any way, this is the actual color variation. Here we have the mountains, alluvial fans coming down, and then all of a sudden you see all this white stuff through here. Can you see these little ridges? Those are very large sand dunes. Basically, this alluvial fan here is coming right from the mountains and coming into a desert environment. Now, I wouldn't have to tell you this was a desert, because what aspect of the picture on the far right-hand side tells you this has got to be a really dry environment?
No trees.
No trees. Do you know what this is? No, I wish. No. It's a farm, or was a farm. Basically what you're looking at here is an area that had been irrigated or planted, but look how the sand has blown right over top of it. This whole area has been abandoned. It's turned into a desert. Folks, this is California. This is not the middle of Africa. So we have issues with drying and desertification in even the United States, as it turns out. Okay? So this is neat, because this is showing you the direction of gravity. In other words, the alluvial fans are all designated this direction, and since these are wind-blown dunes, it's showing you the direction of the wind, which in this case is going that way. All right, so there's the gradient, downslope direction. There's the direction of the wind. Both of those things are going to leave behind evidence showing you what was going on in terms of deposition, and a good, clever sedimentologist, if these things were preserved in the rock record, would be able to reconstruct this very scene based upon the rocks that are left behind. And here again, this is another part of California which is a little bit healthier. See, it's healthier. These are green plots. By the way, so how many of you actually have flown over and looked down and seen these little square patterns everywhere? All right, yeah, that's basically what that is that's the entire agricultural part of our country, which is divided up into sections and quarter sections, etc. So basically what you're looking at here, this is probably a quarter section divided up into quarters, okay, so that's maybe a quarter mile on the side. Never mind that, what you're looking at here now is the alluvial fans coming down from the mountains. I mentioned to you that fans can coalesce, and indeed if you look at this, there are 4 distinct fans here. There's one. There's another one, there's another one, and off in the distance is another one. What they do is they give you a continuous blanket of sediment that drops from the mountains down to the flat areas. And here you can see that the flat areas very heavily occupied by agriculture, and you can see how basically they're starting to lap up onto the fans as you go up here. This is a shot that's at the top of a fan. This is one in New Zealand. I have to tell you, what the alluvial fans are very subtle. Because when you look at them in cross-section, just the way that the sediment comes down, they tend to have a gradually changing slope. They tend to be much steeper at the toe, at the head, and they get more gradual as you get towards the toe. And I have driven on fans before. I remember driving, going from Las Vegas to Los Angeles one day, and I was driving with a friend of mine, and we were just driving for hours and hours and hours, and I kept looking in the rearview mirror, and I could always see Las Vegas behind me for hours. And it suddenly dawned on me that where would you, I mean, it's impossible if you think about it. If you're driving for 100, 200 miles, you're going to go over hills and trees and stuff like that. Well, in the desert, there's no trees. But what we were doing was gradually driving up a slope that was like this. And these alluvial fans can be huge. And because you're always gradually going higher, you look behind you and you can always see further behind. So this shot here, where you're at the top of an alluvial fan, what you're looking at in New Zealand are mountains that are 40 miles away. That lake there is probably 15 miles away, and you can even see towns and cities around here. Why? Because there's a gradual slope as you come up. Okay? That's an important consideration, by the way. And to give you an idea, these are chunks of gravel on the top of the alluvial fan. No one said the gravel had to have a maximum size. These are boulders, as I said, about this big, that you just roll down from the mountains. And look, we are in mountains. Let's see how the sediment is just kind of lapped up right against these vertical cliffs. Beautiful. And incidentally, behind me is a glacier too, so it was a really nice place to view, to visit. All right, here's some important considerations about alluvial fans. All right, they best develop in arid regions. What you want to have is enough water that they actually will have the sediment being washed down periodically, but in flash flood types of situations. And you know how the deserts work, right? You might not have rain for 2 years, but then you get 10 inches in 5 minutes. That washes stuff down from the hills, comes down a huge stream, and is transported like crazy. They're also best developed in tectonically active areas. By this we mean we have to have areas that are rising and falling. I think I have a diagram here to show you what I mean here. Yeah, there we go. All right, so this is a fault. We'll talk about faults a little bit later on. The idea is we need to have a vertical or a fairly high topography here. What happens is water transports things down the hill, down the very steep point where it moves really fast, and then when it hits this lower level here, it starts slowing down. Just hang for a second. Starts slowing down again. Now consider what we talked about previously, right? The faster the water flows, the larger the particles it's capable of carrying, correct? So if you're moving water down in this direction, down a very steep surface, it's capable of moving just about anything. But when you get to this flat part here, the water current slows down. What happens to the large particles? They get left behind. So you start depositing things here, okay? So over time, what happens is you start building up this type of fan deposit. But consider this. If this area weren't a region where the mountains were continually being pushed up, what would erosion eventually do to your mountains? They'll bring them down. There won't be anything left. If there's nothing left, where's your topography? Where's your vertical cliffs? So you need to have an area where you actually have the faults continuing to go up. As the mountain is being lifted up, they're being eroded and giving more and more material. This is an area where material is being funneled down from all sides along the mountains and is being transported and dropped at the base. Where you get that sudden change in slope is where you're going to get deposition taking place. So basically what you're looking at here is this type of diagram where it's coarse here and ultimately is getting finer in that direction. And that, of course, is a cross-section of what the fan looks like in that direction. And again, if I haven't made this clear, alluvial fans can be huge. Remember, I was driving up a fan between Las Vegas and Los Angeles for 2 hours before I realized I was actually driving up a fan. So 60 miles an hour, 120 miles from the toe, and I wasn't even at the top yet. That's how big these things can get. Also notice there's a lateral fining, which you can see very nicely in this diagram through here, and that makes sense too, because as you move from here to there, the gradient is reducing. The lower the gradient, the slower the currents are going to be flowing over top of it, the finer the grain material becomes, okay? And again, this is a key point. Alluvial fans, although they are formed in arid regions, are still formed primarily through flowing water. And here again is where you have to appreciate the time involved in geology. All depositional environments take time to form. And if you've got 2 million years of time, even if it only rains once every 2 years, you're still going to have a significant amount of potential transport of material. Okay, so remember, time is never a variable in this. So while it's formed, the alluvial fans form primarily through the action of water being funneled off, we also have an interesting thing here where we can also have landslides. Landslides, which are called mass flow deposits. That's what the official name is of them. And again, if you've ever been to California, if you ever hear the news in California, when they have a lot of heavy rains in the hills, they always send out their mudslide warnings, or landslide warnings. Occasionally houses get washed away. You've seen the news, you know what I'm talking about. Well, that's because this is an area that's prone for this type of activity. Consider, you might have 2 years of no rain. You still have the sediment washing down the mountains, right, or falling down the mountains. It does rain heavily. All of a sudden, you got a tremendous amount of sediment sitting dry in a river valley. When water comes flowing down it, it's going to start inducing all manner of mudslides and landslides, otherwise called mass flow. Alluvial fan deposits, don't worry about the symbols here. These things can come down a very short distance before they stop. In fact, it's almost like moving cement in some cases. And again, the particles being moved in this case can be huge. I have seen landslides where the boulders literally average about a size like that. And they're coming down literally because they got wet and they got washed down courtesy of some sort of a weird event. Landslides also can be triggered by earthquakes as well, okay? And while we're talking about it, let's just talk now about the sedimentites, because understanding the process is one thing, but ultimately you're going to be asked in the labs to consider what the rocks are telling you, the story they tell you, what their origins are, okay? So starting off up here, at the top of alluvial fans, where the grains are coarsest, where the average particle size is going to be much larger than 2 millimeters, you're going to be dealing with grains that are sub-rounded to angular and large. Now, if you remember how this works, all right, the grains are gravel-sized, but the rock that would form from a gravel-sized sediment that is angular in terms of particle size would be called a breccia. All right, so breccias normally are associated with alluvial fans near the top, near the head of the fan. Coming down further, you're going to get into finer grained sediment that is going to be composed mostly of sand-sized particles. The particles themselves are going to be immature, meaning lots of quartz, lots of feldspar, lots of things. And they're going to be largely angular grains. The proper term for a sandstone that is rich in feldspar with angular grains is called arkose. All right? A pink sandstone for the most part. And as you get further down, you start getting into layers of sediment that are enriched in silt and clay, otherwise known as the mud component, largely red in color for two reasons, and they're going to be deposited as very thin sheets. Now that is called a shale. Specifically, it would be a red shale. Now the reason why the shales tend to be red in color is they're enriched in feldspar, which is pink, but they're also starting to get enriched in iron oxides. Iron oxide, hematite if you wish, colors everything near the surface of the earth in an oxidizing environment anyway, reddish in color. That's the key component here. If this thing forms on the surface of the earth, as it does, it's in an environment that's got free oxygen in it. If you can breathe and not die, it's got oxygen. And if it's oxygen, anything that's got iron in it is going to be colored reddish in color. Hence, red shales. So the three rock types that are associated with alluvial fans, breccia, arkose, shale, reflect the nature of the immaturity of the area as well as the particle size, okay? Immature gravel-sized particles are going to be angular, hence the term breccia. Immature sediment that's sand-sized is going to contain an awful lot of feldspar, hence the term arkose. And red shales, well, red shales form everywhere, at least as long as you have some sort of an oxidizing environment. Okay? Any questions about alluvial fans? All right, let me show you a couple pictures of these things, ancient ones. This is a sedimentologist reconstruction of what we call sedimentary section, showing you the nature of the huge boulders, all angular in size. This is basically what they're looking at here. There's some geologists for scale. This is a single bed of breccia that's got to be what, well, if this person is, say, 5 feet, 5, 10 feet, you get the idea. Huge. This is part of an alluvial fan sequence that formed 300 million years before. It's actually, surprisingly, exposed in a mountain belt where it is now providing the sediment for the next alluvial fan. We're actually recycling an alluvial fan here. The fact that this is an alluvial fan that is hundreds of millions of years old implies that hundreds of millions of years ago at this site there was a mountain belt which was producing this material here. Some more shots. Beautiful, spectacular scenery. Okay, here's the typical exfoliation, the spherical weathering you get in a deserty type of environment. Here you can see it's not so breccia rich. It's more of a sand rich, again, reddish color dominating everything. Oops. All right, and that gives you an idea of the variety of rocks that you get in this region here. Okay. Now with that, we'll turn our attention to rivers. because I want to move through these things fairly quickly so you have a feel for all the different types of environments that are out there. For those of you that are geology majors, when you take the advanced sedimentary petrology class, we will talk about all the different types of rivers that are out there. All right, and we recognize three major divisions: braided, anastomosing, meandering. For the purposes of this class, all I want you to be aware of is that rivers come in a lot of different varieties, but the ones we're going to focus in on are the ones that are most relevant to where we live, and that is the good old-fashioned meandering river that you see here. You know what they look like. Again, if you've ever been in an airplane and flown over anywhere around here, you'll see rivers that look more or less like this. Maybe not always this intensely meandering. This is a small little stream in Mississippi somewhere, and you can see the channel kind of going all over the place. That's what the term meandering means. It wanders around all over. Most meandering river channels can be defined as being a sinuous channel, which means windy, and a single channel for the most part. That separates them from so-called braided streams where you can have multiple channels. Okay, we don't get those around here. We only get this type of thing here. They normally form in very low gradient alluvial plains. Now, again, let me just remind you, an alluvial plain is a flat part of the Earth's surface. Low gradient means it's got a very, very, very low slope. And if you think about it, this is the type of environment that we live on here. Never mind the fact that there are occasionally some hills. If you were to start walking from Dolphin Island all the way up to Montgomery, that entire region, you go from an elevation of sea level to maybe an elevation of about 500 feet above sea level. That's not very much of a vertical relief considering you've just walked over 150 miles. That means low gradient. In that type of environment, this is where you're going to start finding rivers that tend to be meandering. And they come in different scales of meandering. This little diagram here shows you ones that are very sinuous to ones that are not so sinuous. If you've taken a geography course before, you would be familiar with the term mature river, young river, youthful river. How many of you remember those terms? Right. Have you ever taken a geography course?
I took geography 101.
Surprised. I thought most people had to take this in high school. Yeah, I remember this. This would be a young river. This would be a mature river, and this would be an old river. The idea was that the more sinuous it got, the older it must be. That's bogus, incidentally. It has entirely to do with the gradient. The steeper the gradient, the more likely the river is going to be really sinuous, is what it comes down to. And this is something, again, that all of you should be more or less familiar with, or if you're not, get familiar with it now. This is a typical meandering river depositional system. Here is the channel. In this case, meandering all over the place. Every once in a while, you'll cut off one of the loops through a process that we'll talk about in just a second, leaving behind these little crescent-shaped lakes. They're called oxbow lakes. There will be places where sand is deposited in the middle part of the loops. This is called the point bar, and then there will be areas which are eroded on the so-called cut bank side as well. So all these terms that you see here are standard terms that are associated with the geography of meandering rivers. Some of the ones we don't really talk about too much: Yazoo streams. Yazoo streams are small little meandering channels, almost like parasitic channels. We get them primarily in Mississippi, where the name comes from Yazoo, as it turns out, because you have the big Mississippi River, which is the dominant river over this entire region, and then there'll be little small rivers that kind of flow beside it, and they kind of come and go as the river goes. Other important things to consider: levees. Levees are natural buildups of sediment that form when streams flow. Naturally, they occur along the margins here, and of course, these days around here we have more problems with our artificial levees, which are constructs that are made to protect cities. Basically, what we do is we just pile up sediment along the margins of the river. What that does is increase the carrying capacity, allows the rivers to flow up higher than they normally would without flooding. Sounds like a good idea, doesn't it? Problem is, if you build a levee along every part of a river, you never let the river flood, and that means the rivers artificially start flowing higher than they normally would, which is a serious problem. Just about every major river in the United States with levees on it is flowing higher than it would normally be if their levees weren't there, which means when you do have a problem with a flood, you get a catastrophic flood, which is really bad. The other thing to note is that surrounding the channel is a very flat area, the alluvial plain. This is the area that is prone to flooding when a river does flood, okay? So key components here, the channel and the floodplains are where you're going to get sedimentation taking place. All right, so let's talk a little bit about how this all works, especially the channels, because in some ways this is the most remarkable thing about meandering rivers. They meander because of their very nature of the channel shape. And the channel shape is driven by the fact that they're flowing down a very low gradient environment, okay? So, all right, so there's the channel, and surrounding it is the flat part that is called the floodplain, and the channels literally will migrate back and forth over time, okay? If you've flown over, again, this area, you'll see these areas in the middle where you see these sandbars that are deposited inside the loops. These are called the point bars, and let me show you. All right, I want you to imagine now a cross-section from the cut bank side to the point bar side. Meandering river channels are asymmetrical, meaning that they have a shallow side, shallow gradient, and a steep side. Now the shallow gradient side is the point bar side, and the steep side is the cut bank side. This is where you get deposition, and over time what will happen is the point bar will have sediment added to it, and the cut bank will be removed. So over the years you get erosion here and deposition here. All right, I'm going to leave that diagram up here and go on the diagram here to show you what I mean. Here is where you can actually see beautiful evidence of deposition. Each one of these little grooves that you see here shows you where part of the point bar was. And over the years, what you can see is that the point bar has just been growing more and more and more in this direction. This river is in flood, which is why you can actually see some of the little depressions here being flooded by water. All right, so here's how this works. Because the river is asymmetrical, you start getting really weird current patterns. And the cut bank is the side that is going to be most exposed to erosion. The reason has to do exclusively with the depth of water. Deepest here on the steep side. Shallowest here near the top of the point bar. Water depth controls the speed of the current. The deeper the water, the faster the current is, which means the current is fastest here and slowest there. That causes all sorts of problems with turbulence and eddies. Okay, so as you see a river flowing around like this, you find that it's always going to be slowest around here and fastest along this side. How many of you have gone canoeing down rivers? How many of you are lazy canoers where you just kind of sit down and just float and sit there drinking your beer or whatever you're doing? Yeah, a couple hands go up. A couple hands that didn't go up initially when I said how many of you are canoers. Then you will know this. If you want to canoe effectively, what you do is you allow the canoe to follow the fastest path of the water, and that's shown by this dotted line through here. It always swings out towards the cut bank side because that's where the water is deepest. And again, we come back to the idea now that the deepest the water is, the fastest it goes. The fastest it goes, the largest the stuff is capable of depositing, and the more erosive it becomes. So, since this is the fastest, erosion tends to be concentrated along that side. Over time, it is possible for you to literally erode out this type of pattern. Now, that's totally unstable, right? What's going to happen to this side of the cliff? It's going to collapse, kind of like what they're showing you here with the hills coming down. And what you'll find is big blocks of stuff fall down, this falls in, trees over here will also start to fall in. In fact, one of the perils of canoeing, and the way I told you, was that if you are just allowing the canoe to go wherever it wants to, it's going to take you along the cut bank side where all the trees are hanging over like that, since they're gradually falling into the water. And around here you got to watch out for snakes. We actually had a situation once. We had like 5 canoes on a field trip. The first canoe went underneath this and someone said, "Water box in!" And then, of course, everybody looked around and said, watch out for the water moccasin! The next canoe comes down, and by this time the snake's getting really pissed off. And then it dropped into the third canoe that went by. So there was a water moccasin in the canoe and a bunch of panicked people. And to their credit, they didn't do this with the paddles. They kind of went like this and flung it over. And the water moccasin was glad to be gone too, okay? So you get collapse taking place. All right, so erosion here causes also a very interesting current effect, because the currents now flow kind of in a corkscrew pattern. From your point of view, the channel's looking, you're looking at the channel this direction, the current's coming towards you. It's like the currents are doing this. It's a corkscrew pattern. It moves from the fastest to the slowest part. And again, consider what's going to happen. If you're moving very fast, you're capable of transporting very large grain material, sand-sized anyway. What happens when the currents now swing out over here to the shallow water and the currents become slow? What's going to happen to your sediment? Yeah, the coarse stuff isn't going to be able to be carried anymore, so you deposit sand here. Net result is that that's why you're getting deposition on the point bar side. It's the sand component as you're eroding in this direction. Basically, meandering river channels are big sediment sieves. They go through the floodplain, the alluvial plain surrounding the rivers, ripping up all the stuff that happens to be there, the fine-grained stuff, the coarse-grained stuff. The really coarse-grained stuff falls right down to the bottom of the channel where it doesn't move. But the fine-grained stuff will stay in suspension because it's fine-grained. The coarser sand will be transported for a while, but when it gets kind of flung up onto the slow current side of it, will be deposited. Net result is a point bar formed of sand is forming in the middle of the loops as you're eroding on the other side. Fascinating thing happens here. I mentioned that you're going to get some coarse grain material on the bottom. This is a picture from a very old meandering river deposit, very coarse grain material. That would have been formed at the very bottom of the channel, and it gets progressively finer as you go up, which is what you'd expect. Now, you're going to get coarse grain material here that's going to be gravel-sized sediment, but it's going to be well-rounded because this is sediment that's been moved around on a river for a long ways. If it's well-rounded, gravel-sized sediment, you're going to get conglomerate. So if and when one of your instructors says, what kind of depositional environment does a conglomerate form in it, you're going to say river bed, river channel, something along those lines. Don't just say river, because rivers are much more than just a river channel. But in this case, you're definitely going to get conglomerates and things at the base here, okay? I also want to mention to you that we are not done with rivers, because rivers are more than a channel. They also involve the floodplain. Now you should ask yourself this. Why in God's name would you name the alluvial plain around a river the floodplain? It's because periodically the whole thing gets inundated by flood water. Now the most impressive flooding that we've had in memory anyway, in this part of the world, was what happened in the Mississippi, Missouri, Illinois confluence area in the early 2000, or 2003 I suppose is when this actually happened. Actually 1991 is the big one here that took place. Alright, so this is a shot down in St. Louis, looking at St. Louis. St. Louis is located right about there as it turns out. There's the Illinois River, there's the Mississippi River, there's the Missouri River. This is what happened in 1993. What you're looking at is area that got inundated by floodwaters. Now, it may not look all that impressive in the grand scheme of things, but what you've got to realize is that St. Louis is a fairly large city sitting right there. So 500,000 people live in an area like this, and all around them the river is going into major flood stages. What happened? Well, nothing really unnatural. What happened in this situation was more water was flowing into the river than could be contained by the channel. All rivers have a so-called carrying capacity. The river level is fixed by how high the banks of the river are. The minute it starts to get higher than the cut bank, it starts to spill out of the channel and you start to flood onto the floodplain. That's simple. All rivers flood sometimes. The reason why this was such a disaster was that there were so many levees in the environment. I mean, the levees were built in some cases 50 feet above the water level, And the rivers kept flowing and flowing and flowing, and once they got higher than the levees, now you ended up having water that was 50 feet high flooding onto the plain, and it caused devastation. I mean, destruction like you would not believe in this area. For a while, they thought they might end up having St. Louis be flooded. That would have been disastrous with all those people living there and all. But the idea is that flooding is a normal event. And consider what happens, all right? You got a river, a channel, that is getting deeper and deeper and deeper. The deeper it gets, the faster it flows, right? And then all of a sudden you get to the point where the water no longer is contained by the channel and spills off to the sides. You go from water that might have been 50 feet deep to water that's only that deep. What happens to the speed of the water as it spills out into the side, going from deep to shallow? Slows down almost immediately. Net result is the minute the flooding starts to take place, when you get to this point here, you start finding the coarsest grained material being built up right along the edges of the channel because the current has dropped so quickly. You end up literally getting a pile of coarse grained sediment all along the edge of the river. Well, this is where the natural levees come from. And you can understand the Corps of Engineers when they saw this, and they realized that over time, if you have a natural levee now that might be, say, 3 feet higher than the river, that means that the next time a flood takes place, or potential flood, it's got to go 3 feet higher than it was the first time, meaning you've increased the carrying capacity of the stream. And they looked at this and they thought, what a brilliant idea. We'll just go around and we'll just increase the carrying capacity by 100 feet of all the rivers all around the country. We'll protect everything. They'll never flood again. Yeah, it doesn't quite work that way, because what happens is rivers are still going to get more water in them than they can carry, but now what's going to happen is the next time you get a flood, it's going to be 60 feet high, which is what happened here, and next thing you know, it was catastrophic. It flooded the entire region before anybody had a chance. Rivers are meant to flood on a periodic basis, and if you stop them from flooding on a periodic basis, they're still going to flood later on, but next time it's going to be catastrophic as it was here. And by the way, when you get rivers that flood, they're going to be transporting the finest grained material right across the floodplain. Net result is, because all the coarse stuff has been deposited on the levees, the finer grained stuff is making it all across the floodplain. As you see through here, the water is reddish in color because it's an oxidizing environment, fine grained material, iron oxides. This stuff gets deposited behind. What you're left with is a very thin layer of red clay or red mud, which will eventually turn into red shale. And if you have one flooding event every year, over 1 million years of time, what you've got is a very thick accumulation of red shale all around the place. Floodplains build up at the same rate as the rivers do, except where the rivers are depositing sand in the point bars, the floodplains are receiving red shales on the area here. Okay? Okay, folks, well, that was as far as we got last year when we were talking about alluvial fans, rivers, and deltas. And as you can see, I ran out of time last year, as I often do with my lectures. There's just too much stuff to really deal with in one lecture. We have a little bit of extra time left today, so what I'm going to do is continue this narration into 2010, discussing very quickly the important depositional environment known as a delta. Deltas occur where rivers meet the sea, and basically what happens is you have a confined flow, which is the way the water is flowing within a river, and it's moving relatively quickly. As it moves from high terrains to low terrains, it picks up material. Coarse stuff is transported along the bottom as the bed load. Finer stuff is transported in suspension. But when the river meets the sea, you suddenly go from a confined flow, where the water is moving quickly, to virtually no flow whatsoever. The net result is that you end up getting deposition taking place where the river meets the sea. Now, the majority of the material coming out of transport will be the coarse grain material, the bed load primarily, but then the suspended load can be traveling for quite some distance afterwards. All right, now deltas are incredibly important depositional environments. In fact, they're probably the first depositional environment that was ever recorded historically. This is because civilizations have often been founded in deltaic environments. You have to understand that here's an incredibly fertile area, a region that gets water virtually all the time, is subject to periodic flooding, which means that we end up depositing nice fertile new material over a very flat area, the depositional surface. So people have lived at and on deltas from the turn of human civilization, basically. Now, the first people to actually describe deltas were the Greeks, when they were interacting with the Egyptians at the time of Cleopatra and others, they noticed that much of the Egyptian culture was centered on what we today call the Nile River Delta. And of course, from their point of view, the delta was this very large, and it's huge, it's an incredibly large depositional area where the Nile flows into the Mediterranean Sea. They couldn't help but notice that if you looked at the delta from a distance, it resembled a very large triangular shape. And of course, this is the upside down version of the Greek letter delta, hence the name delta. Now, most deltas that we have in the world, especially for the large rivers, are huge. The Nile River Delta, for example, stretches a couple hundred kilometers in all different directions, giving it several thousand square kilometers of fertile terrain. So they're very, very important depositional environments. Now, the neat thing about deltas is that they come in several different varieties, different morphologies, if you wish, and the morphologies are controlled primarily on the interaction between the major processes that control deposition in this environment. If you wish, we call them the major types of energy that's affecting these environments. Those three components are wave energy, and the wave energy is simply the height of the waves, how intense the waves are. Tidal energy, which is the amount of movement that sediment is experiencing as tides come and go, and the amount of energy associated with the river. Now, before we move on and talk about these different processes in some detail, and we're not going to do it today, but we are going to talk about each of these in upcoming lectures, it's important to realize that the energy is tantamount to the amount of movement that is being induced by these forms or these processes. For example, the bigger the waves, the more intense the wave energy is. Where we live along the Gulf Coast, wave energy here is not very impressive. I mean, what are the biggest waves we have here outside of a hurricane? Maybe 2, maybe 3 feet waves at most. There are some parts of the world, for example Hawaii, where the waves are 40 or 50 feet on a nice sunny day. So we say that places like Hawaii have very high wave energy, whereas places like the Gulf Coast have very low wave energy. Tidal energy is controlled by the amount of tides that we have, and again, where we live, we have very little tides. I mean, I think the maximum tidal range we have here is again a couple feet. There are places in the world where the tides are 45 feet twice a day. That means every day, twice a day, water that is 45 feet high comes in and then goes out. That's astonishing, and that's, of course, incredibly high tidal energies. And river input is primarily controlled to the size of the river. The bigger the river, the more material comes down, the more water comes down. Now, the neat thing is that each of these three processes can give rise to different morphological appearances of the deltas. This diagram we're looking at here now shows you the three major types of deltas that we have. The wave-dominated deltas are typically like what we have with the Nile, so they tend to have nice smooth fronts, form in areas where waves are the most important process affecting deposition. Tide-dominated deltas look like a bunch of fingers all interdigitating with one another. We do not have any particularly good tide-dominated deltas in this part of the world, but if you want to go to the Ganges River in India and Southeast Asia, you'll find some classic interfingering deltas like this. And then lastly, we have what are known as river-dominated deltas, and there's no better example of this than the Mississippi. And if you think about it, if we have very little energy in the form of waves or tides in this part of the world, then the most dominant energy is going to be associated with rivers, and of course the Mississippi River is one of the largest and most powerful rivers we have on the planet, so it stands to reason that would be a river-dominated delta. Okay. Now, if you are interested, as I said, river deltas are found around the world. This is a nice little diagram that shows you some of the pictures of some of the major deltas and where they're located. The little inset map also shows you the size of each of the deltas in terms of sediment discharge. And of course, the most important rivers that we have are the largest. The Ganges in India has the most sediment associated with it, followed by the Amazon and the Mississippi and a few other rivers that are worth mentioning in there. So this is well worth looking into if you are interested in deltas. Now let's talk we're not really concerned about the morphologies of deltas here. We're more concerned about the processes that take place here. So let's consider the following. This is a cartoon section of what it's like coming from a river into a standing body of water like the ocean. So the water is indicated by blue here, and the purple is showing you basically the land, and the arrow is showing you the direction in which the currents are coming in. Now remember, we've got a river that is subject to confined flow, which means it is flowing water containing sediment as bed load and sediment as suspended load within this channel. When it gets to the ocean, what happens is that water will spread out on top of the ocean. Now it spreads out on top because we're dealing primarily with fresh water, admittedly with a lot of sediment in it, flowing into seawater. And the seawater is more dense because it's got all these dissolved salts in it. Now when this occurs, you end up having the fresh water floating as a lens on top of the salt water, as indicated by this diagram here. Okay, so you get this little cone-shaped body. The coarse-grained sand is deposited almost immediately because it's being pushed along as bed load, but the finer-grained material can be deposited much further away than where the channel flows in. This gives rise to a very prominent fining characteristic in the sediment. Essentially what happens is fine-grained sediment will rain down from the lens, gradually filling in the bottom of the ocean. Most of the sediment is going to be deposited in the vicinity where the channel is, giving you this classic cone-shaped deposit of sediment that extends well out into the ocean. So, for example, the Mississippi Delta actually has a footprint that makes it right across the Gulf of Mexico. It's astonishing just how much sediment has been deposited in that environment. So, very much like alluvial fans, we end up getting this lateral fining, but the differences here are profound. Most of the sediment that is deposited near the vicinity of the mouth is going to be composed of sand-sized material. It will have quartz in it, yes, but it will also have a bunch of other sediment grains in it. It's not going to be pure quartz sand at all. As you get further away, you get finer and finer grained material, but it's not going to be reddish in color because it's being deposited in a marine environment, and in some cases rather anaerobic. So you end up getting darker colored, greenish colored shales as you move away from where the mouth of the river actually is. Okay, so there's similarities between alluvial fan deposition and deltas, but the actual materials being produced are completely different. Now this diagram shows you some of the morphological features of deltas, and once again, we don't have to go into a lot of detail about this. If you are a geology major, or if you are interested in studying deltas in more detail, you need to be aware that there are subcomponents for these deltas, ranging from the floodplain, where fine-grained material will be deposited on the edges, very much like it does in delta, to distributary mouth bars. This is where you get big bodies of sand that are deposited right where the river meets the actual sea. The pro-delta is the large body of water that is produced in front of the delta, and this is largely underwater. And of course there'll be channels and levees just like there are in rivers, because the processes that are operating here are very similar to one another. Okay, so this is a lot more detail than you have to worry about in Geology 111, but for those of you that are geology majors, this is something you'll see when you get to the upper level sedimentology class. Now, as I did previously with alluvial fans, I want to introduce to you some of the types of sedimentary rocks that will be produced in these environments. As I've already tried to allude, the distributary mouth bars, where sand is being deposited in front of the river mouths, but it's not going to be as clean as quartz sand on the beach. The energies here are different. There's a lot more stuff coming down. This is the environment where you'd expect to see some quartz grains, but a lot of other darker colored grains as well. This is that classic environment to find lithic sandstones, those salt and peppery type of rocks that you see in the lab. By the way, this image you see here is a picture of what's interpreted to be a distributary mouth bar. I'm not sure where that is, somewhere in the southwest United States, but the thing you see circled there is a human being. That is a huge body of sand because the delta that formed it was probably huge. The floodplain is another area where you're going to get a lot of sediment being produced, and on an alluvial fan, on a river, the floodplain sediments are composed of reddish colored shales, but again, Here we don't get a lot of reddish colored shales because we don't have deposition on land for the most part. We have it deposited just below sea level. And in situations like this, you're going to have a lot of anaerobic conditions. That means iron will be present as Fe2+, giving a greenish color. There's also an awful lot of organic material can be produced here. These are very swampy areas, and of course the swampy material is being having a lot of carbon added to it, giving rise to anaerobic conditions and a lot of dark color to the sediments being produced. So hence you end up getting black or gray colored shales in a situation like this. Okay. Now, one of the neatest things about deltas, and this is a good thing to end on here, is talking about how rapid sedimentation is in these environments. What you're looking at here now is a map, a simplified map showing the changes of the Mississippi Delta over the last, probably around 4,000 to 6,000 years, okay, 5,000 years, somewhere in that general range. The line you see in yellow is the present area of sedimentation, and it goes back to about 1400 AD. The green line shows you where the front of the sediment was from 700 AD to 1400 AD, and it goes back to about 3400 BC. The time the pyramids were being built shows you where the deposition of the Mississippi River was taking place. And even though that sounds like a long time ago, you have to realize that for geology, that's like yesterday, okay? Now, the neat thing about this diagram shows you that in the last 5,000 years or so, there has been an incredible amount of fine sediment deposited in the Gulf of Mexico. That's because this is a big river carrying a lot of sediment, and all the sediment gets dumped where the river meets the sea. Over time, what happens is the river will continue to expand further and further and further out into the sea. Every once in a while, however, there will be a sudden shift, because the further the river has to flow into the ocean, the more likely it is to flood. And if it floods, it's quite possible the channel could suddenly shift from one channel to another. Now, what you see in this diagram are two rivers: the Mississippi River, which flows through Baton Rouge, New Orleans, and into the Gulf of Mexico, and the Atchafalaya River. The Atchafalaya River actually meets the Mississippi River in the vicinity of Vicksburg, just north of Baton Rouge. The Corps of Engineers, many, many decades ago, put an artificial channel through that would force the Mississippi River to flow through Baton Rouge into New Orleans. The reason was to maintain the shipping channels in that direction. There's a tremendous shipping industry that occurs in both Baton Rouge and New Orleans. And if the river would suddenly shift to go down the course of the Atchafalaya, then what would happen, of course, is that we would lose all those port facilities. And somebody thought it was a good idea to keep the river flowing in the same direction, because it would be expensive to continuously shift where all the docks and the port facilities were. There's a problem, however, with this, because the further the delta has to flow into the sea, or the river has to flow into the sea, the wider the delta is, the more likely it is to back up. Net result is that by forcing the river to go one direction, they've actually put this area in a very, very dangerous situation where river flooding can be catastrophic, as we saw with things like Hurricane Katrina, which hit New Orleans back in 2005. Yes, that was a storm event, but it was also a failing in the engineering that was done for the city, so it did have some problems. Anyway, with that now, I think that's the last slide. Yes, it is. Okay, so here's what we need to do. Hopefully by now you will have watched this lecture and made notes for it, because this is material that will be accessible on any upcoming tests. If you did not understand everything I was saying, see me in class the next time we meet, and certainly download and read web lectures 15A and 15B, okay? The next time we meet, for this year anyway, we're going to be talking about more sedimentary rocks. We're going to start introducing some marine rocks, and I'm going to outline the first of your assignments in Geology 111. It's on contour maps, so I'll give you some feedback on what needs to be done for that. And I strongly encourage everybody does the assignments, because that's a good way to pad your grade in this class. Anyway, with that, I will say goodbye or good night, whatever time it happens to be when you're watching this.